Okay, so in this video we'll prove a couple more theorems following on with the same circle ideas as in the last couple of videos. So first theorem is like this. Okay, so we've got a continuous injective map from the n-dimensional ball to the n-dimensional sphere. Then the claim is that f of, we look at the open ball inside the closed ball, I want to claim that that's actually an open set. Okay, so notice this is certainly not kind of an obvious or automatic thing. For a continuous map, it's by definition it's true that the pre-image of an open set is open, but it's not necessarily true that the forwards image of an open set is open. So there's definitely a lot to prove here. Okay. Okay, so what we're going to do is start by setting U is Sn, and I remove f of Bn. So that's open, notice, because it's Bn is compact, so f of Bn is compact and therefore closed, and so this is an open set. And that's oh yeah, sorry, no, that's not what I meant to say. This is for U. I'm just going to remove the image of Sn minus 1. So that's open, and has the homology of U is isomorphic to the homology of S naught, which is z squared in degree 0. Okay, so you've got z squared in degree 0 and 0 is everywhere else. Okay, so so that's the homology of U. So now I'm going to divide U up into two parts in two different ways. So the first way is to just be from the fact that the homology is z squared in degree 0. We find that U has two path components. So I'm going to put V is the path component of f of 0. Okay, remember f is a map from the whole ball. So in particular, you've got the zero vector inside this ball, which is not in the sphere. So f and f's injective, so that means f of 0 lies in the set U. We can have the path component of f of 0. I'm going to call that V. And W is going to be the other path component. And so U is the disjoint union of these open sets U and V. So remember, path components in an open subset of the sphere are themselves open. So these are both open sets, like so. And so now U is the disjoint union So that means the homology of U is the homology of V, direct sum the homology of W. And so homology of U doesn't have anything in positive degrees, so the homology in V and W don't either. So that tells us that these open sets V and W, they're both acyclic. Okay, so that's our kind of first step. Second step is going to be to divide U into two open sets, well, into two sets, two connected sets in a different way. You call them V prime and W prime, and then we have to show that V prime and W prime are actually the same as V and W. Okay, so I just wrote again what we said a second ago. We've got our U is Sn, and we've removed the boundary sphere. There's two path components, V and W, V being the component of f of 0, and both of these are open acyclic sets. So now let's put V is image of the open ball, and V prime, and W prime is what I get by removing the full image of the full closed ball. Now, so what do we know here? Okay, so we know f of Bn is compact. So W prime is open, and also W prime is acyclic. Okay, so that was a big theorem we proved a couple of videos ago, that if you take Sn and remove the image of a ball, then it's always going to be acyclic. And then this V prime, well, we don't know whether that's open or not. I mean, remember the statement of the theorem is that to say that f of OBN is open, so we need to prove that V prime is open. We don't know that yet, but we do know so any 2 points in V prime are f of x and f of y, for some points x and y in OBN. So then you could join them in OBN, certainly by a linear path. So you've got 2 points here. Choose corresponding points in OBN. You join those by a linear path. You apply f to it. You get a path from fx to fy. So this gives a path between them. So that proves that V prime is connected. Path connected. Okay. Okay. So now, so we've got these sets V and W here, and these sets V prime and W prime here. And what I want to prove is that V prime is the same as V and W prime is the same as W. Okay. So so W prime is acyclic, so in particular it's connected, and V prime is connected. So let's say if there was a path, a point in V prime, there was any path from a point in V prime to a point in W prime, or path in U, then that would mean so then what would that tell you? I mean, you've got any point in V prime, or you've got any 2 points in V prime can be connected by a path in V prime because V prime is connected. Any 2 points in W prime, they can be connected by a path because path within W prime, because W prime is acyclic, therefore connected. And so if it's possible to cross over from any point in V prime to any point in W prime, then you can get between any 2 points whatsoever. Set U, which is V prime union W prime, that would be connected. But that's false. Remember, we said that this U splits into 2 different path components. So there's no So we conclude that there's no paths between points in V prime and points in W prime. Okay, so let's just take stock again. Here's what we've got. We've got our U split as V union W, where these are both open and acyclic and in particular connected. It's also U is also split as V prime union W prime disjointly, where V prime is this set here, which is connected, and the W prime is this set here, which is open and acyclic, so in particular connected. Okay. Now, okay, so V prime's connected, and it contains the point f of naught. So everything in V prime is connected is connected by a path to f of naught, and so it lies in the path component of f of naught, which is V. Okay. So now let's suppose A is in V. So A is connected to f of naught by a path in U, right? That's because V is by definition the path component of f of naught, so such a path exists. To the point here, which is in V prime, but this cannot cross between V prime and W prime, right, by what we said here. So the point A must actually lie in V prime. Okay. So this is showing that V is contained in V prime. Therefore, V equals V prime, and V is open. Therefore, V prime is open. And that's what we wanted to prove. V prime was by definition the image of OBN. So f of OBN we see is open. Okay, so that proves this theorem that we stated. Okay, we've got a map from the closed n ball into the n sphere, and the image of the open n ball is open. Okay, so now we can prove this theorem that's sometimes called invariance of domain. Let's state this slightly differently. So let U so we've got some open subset U of Rn, and let F from U to Rn be continuous and injective. Then the claim is that f of U is also open. Okay. Of course, if you want, you can say, well, if you take any open subset of U, you apply f to it, then by the same logic, then f of that subset is also open. In other words, f sends open subsets to open subsets. Okay. And so the proof of that, well, so suppose we've got some point B in f of U, then then you just take some point A and U that maps to it. So then the the open ball around A of radius epsilon contained in U. Okay. So then we look at the closed ball of half the radius, let's say to Rn. Okay, and yeah, so a previous theorem was about the sort of closed ball of radius 1, but of course it doesn't really matter if we change it to a closed ball centered at a different point of different radius. It's essentially the same. So a continuous injective map like this from a closed ball into Rn. So this image of this open ball here of a slightly smaller radius is, well, it's open in officially Sn by the previous result. Okay, this is a subset of Sn, but it's contained in Rn. We are identifying Rn with a complement of a point in Sn in the usual way. So it's going to be, if it's open in Sn, it's going to also be open in R. Okay, and it's contained in F of U. Okay, okay. So this and of course this point contains B. Okay, so we've shown that for any point B, we've got an open set which contains B and is contained in F of U. So if we take the union of all these sets here, one for each B, then that's an open set, and that's just going to be the same as F of U. Okay, so this is that's what we need in order to prove that F of U is open.